name is Anthony Spradling, and this is my Lab 4 physics submission for Physics 2211. The purpose of this lab was to compare the motion of a spring mass system to a computational model of the system in GlowScript as it oscillates randomly. The fundamental physics principles used in this lab were Newton's second law, energy principles, and net forces. In the end, we were able to compare the computational model with the tracker data, and we found that their positions were similar. One important difference we saw was a loss of energy in our tracker data, but this is to be expected in real-world conditions. There are other reasons for the minuscule difference in position data, but we will discuss them later in this presentation. Some of the main physics ideas in this experiment were the position update formula, velocity update formula, and energy formulas. We use these in conjunction with F-net equations to find information we need to iterate for in our experiment. Our F-net equation is also on display here, as the net forces of gravity and springs are present. Although this is only the model at one point in the experiment, it is a good representation of the forces overall. Here we have physical models we produce from Tracker. We were able to get position data over time from the video on the right, and we used the red dots to mark these positions. As we can see by the graph on the left, the mass has a vertical and horizontal oscillation caused by the spring. The point of this data was really so that we could use it as a comparison for our model under ideal circumstances. Here's some important information for our computational model. We define the system as the mass, the spring, and the earth, and the surroundings is everything else. Everything else in this case is really nothing because there is no potential energy or kinetic energy coming from any other sources. This is the GlowScript computation. We would define the initial conditions with an arrow, and they were derived using the velocity equation shown here. The initial position of the mass was taken from the tracker data. Here we also have marked the energy equations we use, the spring force equation, net force equation, velocity update formula, position update formula, and energy change equations. Hence we said that everything was inside the system. That means that energy should be conserved and no work is done. So as the mass moves, the total energy stays the same, and it transfers between potential energy in the spring, potential energy from gravity, and kinetic energy from the motion of the mass. Here we have the outputs of the GlowScript model compared with the data we got from Tracker. Here it looks like there's a significant difference between the position of the model, but if we look closer we can see that these differences are very minute, only consisting of 2 centimeters at most. For the X position, we see that the model oscillates, and over time they kind of diverge from one another. This is consistent with what we know about reality, because in truth there are other factors that do work on the system and remove energy, so the fact that it cannot keep pace with the tracker model makes sense. This is different from the differences we see in the Y direction. My hypothesis is that there are some differences in the tracker setup with the true distance in the model. We had to give Tracker a distance to measure everything from, and in my opinion, the way that we were asked to do it was very haphazard. We should have been given a ruler or something we know instead of basing the entire direction on the spring because it was moving. Another thing of note is that the energy for the model doesn't seem to add up. We should see a more consistent fluctuation, and I think this comes back to a problem with the gravitational potential energy. Some sources of error that will explain these differences found before are wind resistance, loss of energy through the spring is heat, incorrect inputs of tracker alignment or human error, and skew from the camera that would cause perceptual differences. So for the first question, if the energy principle is satisfied, I'd say yes for the model. We expected that the change in energy of the system would be 0 because there is no work being done on it. It's a little weird how our model looks, but the principles make sense. We would expect something more similar to the model on the right, where the energy of the spring and the energy of gravity cancel out as the model oscillates, and whichever side the kinetic energy is on would have a shorter head for the corresponding assigned energy. In this question, we estimated the period of oscillation based on the tracker data for X and Y. I did this by finding the time it would take to do one oscillation in both the X direction and the Y direction. We found that these differences were kind of interesting. My hypothesis for why this is because of the random motion. I think that the angle the mass was released at could have some effect on this, and it's possible that these inaccuracies from the tracker model also had some effect. That's it for my Lab 4. Thank you.